lecture is on the topic of optimality and coerciveness of a given function of several variables. In this lecture, we will try to discuss three particular definitions of optimality. Those are local optimality, global optimality, and strict optimality. After defining these three definitions of optimality, we will try to discuss existence of an optimum point. Towards this, we will require two notions. Those are coercive functions and compactness of a given set. Slowly, after the existence result of a minimizer, we will try to characterize local minimum point for an unconstrained optimization problem. Well, if we look back our class note for the last day's lecture, we can see that we were trying to discuss about a few convexity preserving operations. We have in particular discussed 5 convexity preserving operations. Those were positive weighted sum of a finitely many convex functions is a convex function. We have also seen that if we take pointwise maximum of finitely many functions, then you will get a convex function out of it. We have also seen that if we consider partial minimization of a given convex function, partial minimization, by that we mean with respect to a few variables of the argument variable of the given convex function, if we minimize the function with respect to those chosen variables, then you will get a convex function again. So partial minimization of a convex function is again a convex function. And also two particular compositions of convex functions were discussed, for which you will get a convex function as an output of the operation. Those were convex composition with the affine mapping is a convex function, and also if we consider a monotone non-decreasing convex composition with a convex function, then also you will get a convex function. So these were the few operations that we have discussed on last day's lecture regarding convexity preservation. And towards the end of the class, we have started discussion on unconstrained optimization problem, and we have seen two particular examples in which we have observed that local minimizer or even global minimizer, they do not exist, and therefore prior to identifying a local minimizer for a given function, it is truly important that you please certify whether this function, that is an objective function of the given problem, is having a solution, is having a minimizer or not. Fine. And towards this, in today's class we will involve rigorously in this existence result for a local minimizer for a given unconstrained optimization problem. Fine. So let's start our class with the three definitions of local optimality. And by optimality in our course, I have already mentioned, by optimality we will discuss only minimality. We will discuss only minimizer, because minimum of a function f, it can be posed as a maximization problem, maximum of minus of fx. And therefore, without loss of generality, if we discuss our theory for local minima, that will be equally applied for local maximum for the objective function as minus f. Fine. Well, so let's start our class with the notion of local and global minimizer. By local and global minimizer, I guess we all know what do we mean by them, but still let us refresh, and then we will see that there is really an anomaly, and which has to be somehow swept out, and then only you can see that a local minimum will not be a global maximum for a function. Well, so let me discuss at first, let me define, and let me move ahead. Well, so let me at first let me define what do we mean by a local minimum. By a local minimum or local minimizer of an unconstant optimization problem, here the given problem, given problem in this lecture is the unconstant optimization problem, which is a minimization problem, minimization of a function of n variables. The variable x is here n dimensional. By a local minimum of this problem, we mean a point x bar is called a local minimum if there exists a neighborhood, say ball of radius delta, such that the function value at x bar is less than or equal to function value at any x inside the neighborhood. Here delta is some positive quantity. Fine. And by global minimizer, we mean a point x star for which you have fx star less than equals to fx for any x in the entire n-dimensional Euclidean space or in the domain of the definition of the objective function. Fine. Now with these two definitions of local minimum and global minimum, we will have an anomaly as follows. With these two particular definitions, you can note that a local minimizer can be a global maximum of a function. This is possible by the definition of local minimum and global minimum. And what do we mean by global maximum? By global maximum, we mean a point x star for which fx star is greater than equals to fx. So if you reverse this inequality and this particular inequality, you get respectively the definition of global maximum and local maximum. Fine. So here, for instance, let me give you an example where you will see that a local minimum is a global maximum. Let me consider the following function. You can quickly find a graph in which you will find local minimizer is a global maximum. For instance, here is the location 1, here is the location 1, then it is the point 1 1, then you consider for x less than 1, you consider x, and in between 1 to 2 the function value is equal to 1, and after 2 you consider that line in the graph follows 3 minus x, precise expression for this function. Fine. Now for this function we note that any point in between in the open interval 1 to 2 is a local minimum and also global maximum. Therefore, a local minimum can possibly be a global maximum. However, it is a common intuition. You find the minimum most of the local minimum value that will give us a global minimum. This common intuition is although not true in general. However, in few cases this is possible that you find out local minimum, the point of all the local minimum, and you get minimum most of all the local minimum values, you get the global minimum. And this is a common intuition, but here we note that a local minimum can also possibly a global maximum. And why is this coming out is due to the inclusion of equality in the definition of local minimum and global maximum. If we would have somehow considered this inequality with strictness, then this anomaly that a local minimum is coming out to be a global maximum will not be seen, and therefore the notion of strict minimality or strict local minimizer and strict global minimizer was found. Let me define strict local minimum and strict global minimum. By strict local minimum, it is the same definition of local minimum with strict inequality. Let me just quickly write it out. There exists one neighborhood such that f of x bar is less than fx for all x in the neighborhood. If there exists a neighborhood of the point x bar, then we say x bar is a strictly local minimum. Similarly, by strict global minimum, we mean a point x star so that f of x star is strictly less than fx for all x in the domain of definition of the function. Then the point x star will be called as a strict global minimum. Fine. Now after this definition of strict local minimum and strict global minimum, let me repeat again the important point that I was discussing on the last day, that broadly in optimization problem, although the definition of the optimization problem asks you to find a global minimum, however this is rarely possible. There is a very less number of problems for which you can reach at a global minimum, and this is rarely possible practically, and therefore we will endeavor, we will put our entire effort to find at least a local minimum. And even further, not only local minimum, later we will see that after developing the optimization algorithms, we are ending up with finding a point at which the gradient value vanishes. So broadly in optimization problems, almost all the algorithms developed till today, they are satisfied with finding a local minimum, as identification of a global minimum is not an easy task, and therefore by a minimizer we will just think it is a local minimizer. In our course, we will be satisfied enough to find a local minimum. And again, as I have said, out of the local minimum, in some cases, in some functions, for some objective function, you will find that out of the local minimum, you get the minimum, most of the local minimum, you get the global minimum. However, this is also rarely possible. You can just consider an example, like let me just draw out, you can find an expression for this function. Let me consider a function for which you have a local minimum but you don't have a global minimum. For instance, let me consider a function let's suppose, let me draw a function like x on the left hand side, then you consider a function on the right of one like this straight line, and afterward then again you straighten it to up to infinity. Now for this function, you note that this point is a local minimum but it does not have any global minimum. And under which condition then can we ensure a function is having a global minimum? And this is our endeavor in the next discussion, where we will try to discuss about the existence of a local minimum. And towards this, we require to call here the extreme value theorem or the Weierstrass theorem that we have discussed in our undergraduate mathematical analysis topic. Let me recall this result once again, and afterwards we will move further. That result for existence of a local minimum or a global minimum is followed from the Weierstrass theorem. It says that any continuous function defined on a compact set attains a global minimum. Here X is a subset of, in general, X is a subset of the n-dimensional Euclidean space. So for n variable problems, this result is equally valid. Let me speak a few words here. Here you note that this result is truly restrictive, because mostly in our optimization problem, maybe our constraint set or the domain of the definition of the function might not be a compact set, and in that case the result is not valid. For instance, last day I was trying to discuss about this problem, minimum of the function x over the interval 0 to 1. Here the domain of definition of the function is 0 to 1. We have to optimize this function x on this domain 0 to 1, or rather you consider minimization of the function e to the power x that I was discussing on the last day. Then here your restriction of the variable x, it was unrestricted, and therefore here you note that neither this open 0 to 1 nor the entire real number line is a compact set, and there can be arbitrary set as a constraint set of your optimization problem, and therefore this result, Weierstrass theorem regarding existence of local minimum, is truly restrictive. It is applied only for a compact set. By compact set, if you recall, it is a closed and bounded set. Not necessarily your constraint set of the problem is a compact set, and therefore this is a restrictive result. And now, to overcome this issue, to resolve the issue on compactness, there is a little deviation of this result with the help of the notion of coerciveness of a function. By coercive function, we mean a function f from Rn to R is called coercive over Rn if you have, or the definition should go in a broader sense, although we are discussing here only unconstant optimization problem, but let me discuss the definition in a broader sense. The definition is eventually defined on a subset of Rn and is called coercive, and here this x is a subset of Rn, is called coercive on the set capital X if you have limit once the variable moves to infinity, where x is belonging to capital X of fx is equal to positive infinity. That is in a sequential criteria, that is if for any sequence xk, a sequence in capital X with this xk moving, norm of xk moving to infinity, we have limit of k tends to infinity if xk is equal to positive infinity. This is a sequential characterization of coercive function. Now with the coercive function, the existence result that I was trying to mention is the following. Let capital X be a non-empty subset of Rn, and we consider the objective function to be continuous on capital X. Be continuous. So we are considering a continuous on a given non-empty subset of Rn. Then the result says that if any of the following three conditions holds, that first condition, if X is compact, and that is precisely your Weierstrass theorem, and or either this, or you have X is, if it is not compact, but if it is just closed, it can be unbounded. So if it is closed, and if is coercive, or you have at least one sublevel set of the function f such that that sublevel set is compact. There exists one alpha scalar such that this is compact. If any of these three conditions holds, the first condition essentially is the Weierstrass theorem. The second two conditions are not Weierstrass theorem. In a second condition, we have a relaxation on compactness. If it is closed, the set capital X is closed and F is coercive. Or even you forget about coerciveness or compactness, if any of the sublevel set of the function A is a non-empty and compact subset of Rn, then the function must have a global minimum in the set capital X. The set of minimum, the set of minimum, here this minimum sense is global minimum, if on X is non-empty. Fine. We are not going to prove this result. Interested ones can visit the Dimitri Bartesica's book on the title Nonlinear Programming, page number 755. You please have a look if you are interested to learn the proof of this result. Anyway, so here let me spend a few time, quite a bit of time, let me spend for coerciveness of functions. And before getting into a few examples on coercive functions, let me also speak a few words about this result. Here you note that at first this theorem does not give possible candidates of minimizers. It just gives existence of minimizers. However, we will develop soon methods to find possible candidates. Although this particular result gives existence result, but this existence result will not be helpful for methodical development. And therefore, this result just ensures that the problem has a minimum point. However, this result does not give any clue about possible candidates of minimizers. This is a first note. The second note, although you may think that this result is again little restrictive, that earlier in the Weierstrass theorem we were needing capital X to be compact, the function f to be continuous. And here again you are considering except compactness we require closedness and the function to be coercive, or otherwise you also require non-empty and compactness of at least one sublevel set. Again they are again restrictive, but a little bit enhanced analysis from this result will reveal that this result is truly helpful for the existence result, and this is not really be requiring that capital X to be closed. It will not be requiring at least one of the sublevel set is non-empty and compact. This is due to the following result, that once the function f is coercive, and a characterization of coerciveness is the following. Let me just write out characterization of coercive function, and then from that result we will see that if a function f is continuous and coercive on the entire n-dimensional Euclidean space, we don't have any restriction like capital X to be compact, it has to be closed and so, and those restrictions are not required. We just require continuity and coerciveness of a function to ensure that it has a global minimum. How? And that is really followed from this result, from this existence result. How is it? For that we need a result on characterization of coercive functions. It is one if and only result. It says the following: let f be continuous on the entire n-dimensional Euclidean space, then the function f is coercive if and only if for every alpha the corresponding sublevel set X belonging to Rn such that fx is less than equal to alpha is compact. Fine. Now with the help of this result, characterization of coerciveness, we note that a function once it is coercive and continuous, the function on the entire n-dimensional Euclidean space, the function must have a global minimum. How? Let me just prove not this result, and the result that I will be writing now, that is again an existence result, existence theorem. Let me call it as existence theorem 2 and earlier theorem as existence theorem 1. Fine. And here in the existence theorem 2, we have the following statement that if f is continuous and coercive on Rn, then f has a global minimum. Fine. How this is followed from a simple one-line logic. Here you note that if f is continuous and coercive, due to the earlier result on characterization of coerciveness, we note that this sublevel set, you consider any x0 in Rn, and you consider this sublevel set of all points in Rn such that fx is less than equals to fx0. Now note that this set capital S is a compact set. This is due to the fact that corresponding to alpha equal to fx0 or alpha naught equals to fx0, we note that the sublevel set fx less than equal to alpha naught is a compact set because the function f is coercive, and therefore capital S is a compact set. Now on this capital S, your function f has a global minimum due to the Weierstrass result, and once in capital S you have a global minimum, that will be indeed global minimum for the function f, because in the entire space, in the entire n-dimensional Euclidean space, whatsoever minimum you have, obviously that minimum is indeed minimum of the function f over the set capital S, because you are operating here the minimum operation, and therefore the function f must have a global minimum in the entire n-dimensional Euclidean space. Fine. Now here again we note that although all these results are existence results, but they do not give any clue regarding what is a possible candidate of a local minimizer or a global minimizer. We'll move ahead soon regarding identification of or characterization of those points or in which the function might have a global minimum or at least a local minimum. But before that, as I have spoken, I have spent quite a bit of time regarding coercive functions. Let me give a few examples on coercive and non-coercive functions. Let me take a function norm of x square. Let me consider the function of two variables f(x1), x2 given by Euclidean norm square. Now this is trivial to check that this function is coercive. Here my variable x is two-dimensional and it has two components x1 and x2. We note that limit norm of x tends to infinity of fx is nothing but limit norm x tends to infinity of norm x square of it, right? It is Euclidean norm, two norm it is. And here also we are considering only two norm of x, and obviously this is positive infinity, and therefore this function f is coercive. Now let me ask you a question that if I consider a linear function, let's suppose I have a function of two variables f of x1 x2 given by a1 x1 plus a2 x2 plus b, where a1 a2 b are real numbers. a1 a2 b are real numbers. Fine. Now is this function coercive? Think a little and pause the video, and afterwards you check the solution. A linear function can never be coercive. Why is this? This is due to the following fact, that we know that without loss of generality, if I assume that is a1 not equal to 0, you could equally take
a2 not equal to 0, because if you have a1 a2 both of them are equal to 0, this function is a constant function and it is not obviously a coercive function. So here, without loss of generality, let me assume that a1 is not equal to 0, at least one of them, at least a1 or a2 is not 0. I am assuming only a1 not equal to 0. And once we are assuming this, then you follow this sequence xk, and it has obviously two components. Xk has x1k and x2k, and you consider this sequence that x1k component is minus a2k divided by a1. I am following this particular line, that a1 x1 plus a2 x2 plus b equal to 0. Here you note that by following this particular line, that a1 x1 plus a2 x2 equal to b, this line can lead me to infinity, right? And obviously, if I follow this sequence, that I take the first component as this and second component as k, so I am considering that integral values here. Let's suppose here is my 1, here is my 2, and so on, and accordingly these are the sequential points. These are the sequential points, right? So if I follow these sequential points, then accordingly I can reach to infinity here, following this particular sequence xk. Now here let this xk for any k in the natural number set, we follow this sequence, and then note that on this sequence, which is eventually lying on this line, a1 x1 plus a2 x2 plus b is equal to 0. Okay, fine. This is my kth sequential point. And if I follow this sequence, then you note that norm of xk is tending to infinity as k tends to infinity. This is very easy to check. And then we note that limit k tends to infinity f of xk is equal to 0, because along these sequential points, at any point in this sequence xk, the function value is equal to 0. And therefore here we note that along a sequence, although we are reaching to infinity, but the function is not reaching to positive infinity. The function is still in 0, and therefore this function is not coercive. And therefore you can now observe, here I have taken only function of two variables. You can take any function of n number of variables, and in that case accordingly you take sequential points on the plane a1 x1 plus a2 x2 plus till a n xn plus b equal to 0. On that plane you take sequential points, and on that plane you can reach to infinity. But again you note that the function is still at the 0 value, and therefore the function f is not coercive. And therefore we can conclude here with this calculation, that we can conclude that any linear function is never ever coercive. And then with an extension of the same line of logic, can you be able to check whether this function f of x1 x2 is given by x1 square minus 2 x1 x2 plus x2 square, is it coercive? Think a little, and again it is not coercive, because this expression is x1 minus x2 square, and which is equal to 0 on the line x1 equals to x2, and therefore this function is not coercive. Fine. Can you please write on your own here that why, in a mathematical way, can you write why it is not coercive? Although I have mentioned the logic, but you please practice this mathematical way of writing. Whenever you will write some research article, and if you involve some sort of mathematics, your mathematics should go with exact mathematical expressions of your thinking. Otherwise this is not appropriate. And in any research article, unless your mathematical writing sharply with mathematical expressions, mathematical examples, you cannot prove, you cannot establish a particular result, and that result eventually will not be acceptable in any journal. So it is really suggestive, if someday you are going to write some research article, then you try to learn how mathematics should be written, and how to materialize your thinking in a mathematical way, how your thinking can be established with mathematical expressions. Anyway, let me take another example. Consider this function if x1 x2 is equal to x1 to the power 4 minus 4 x1 x2 plus x to the power 4. Now for this function, let me just give you a hint, and this is really a coercive function, and let you check why is it coercive. Now let me hint out here that this expression can be written as x1 to the power 4 plus x2 to the power 4 times 1 minus 4 x1 x2 divided by x1 to the power 4 plus x2 to the power 4, provided your point is non-zero. So at any non-zero point, this expression is this much, right? And we note that once your x1 x2, once it is moving towards infinity, then what will happen? That this first expression will obviously move towards infinity, right? For norm x tending to infinity, you have this, and you can also check that this expression positive quantity always and lies in between half and 1. Fine, hang over a little with inequality calculations, and with the manipulation of inequality you can prove that this expression is in between half and 1, and this expression moves to infinity as norm x tends to infinity, and therefore this entire product moves to infinity as norm x tends to infinity. Fine. Now for more examples on coerciveness, visit the book, a very authentic classical book that has come out in the year of 2014 with Mathematical Optimization Society and Siam together. From this series, you have a book written by Amir Beg on the title An Introduction to Nonlinear Optimization. Now, as the existence theorem do not give possible candidates of optimizer, next we will develop a few necessary and sufficient conditions for optimality for smooth optimization problems. Let's start with the concept of descent direction, and then we will derive first order and second order necessary conditions for optimality. And again, first order and second order, they are essentially some conditions involving, in first order you have first derivative, in second order you will require second derivative or the Hessian of the function. So first order and second order necessary optimality conditions to derive, we at first try to discuss a little about the notion of descent direction. What do we mean by a descent direction? By descent direction, broadly we mean a direction along which function's value decreases locally. Now how can we mathematically write this? By decreases locally means at least you have a local neighborhood, that means you have a small distance on this direction. Let me suppose a small distance, let me say I have a distance delta greater than 0. So here we know that any point on this direction can be presented by x bar plus lambda d, right? Yeah, where lambda is a scalar quantity and lambda greater than equals to 0. Any point on this directed line is given by this expression, vectorial expression. X bar is a vector plus lambda is a scalar into d. D is a vector given direction. Now here by descent direction, d is a descent direction. What do you mean? You have at least a small value of length, small value of this lambda, such that what you have is the function value at any point till that amount of length. That means at any point you calculate function value in between this x bar and x bar plus delta amount of length into the direction d, such that f of x bar plus lambda d is less than equals to f of x bar. By decency of this direction d, we mean that there exists a delta greater than 0 such that f of x bar plus lambda d less than equals to f of x bar for all lambda in between 0 to delta. And these restriction essentially means that at least locally, at least in a local neighborhood of the point x bar, along the direction D, the function value degrades, the function value decreases. Let me just write here descent direction. Let me consider a point for a given point, a point and a function for a given point x bar belonging to Rn. A direction D is called a descent direction of the function f if there exists some length, let me say here epsilon greater than 0, such that f of x bar plus lambda d is less than f of x bar for all lambda belonging to 0 to epsilon. Fine. So if function value decreases at least locally in the direction of D, then the direction D is called a descent direction of the function f at the point x bar. Fine. Now let me write out here a characterization of descent direction. Let me see how much time do I have. Oh, anyway, time is up somehow. So on the next lecture, then we will try to start with a characterization of decency of a given direction D, and there we'll see that along a direction D, if the directional derivative is less than 0, then the function must have a decency. The function must be decreasing in nature, at least locally, in the direction D. This is very trivial because this, directional derivative that gives instantaneous rate of change along a particular direction, and instantaneous rate of change, if that is less than 0, obviously along that direction the function is decreasing, and therefore along the given direction D, if the directional derivative of the function at the point x bar is less than 0, then the function must have a decency along that direction. The function must be degrading, the function must be decreasing in nature, at least locally, in the given direction D. Fine. And that will be your first order decency condition. And if somehow the derivative value is equal to 0, the directional derivative value is equal to 0, then with the help of the Hessian matrix as well, we will be able to characterize descent directions. And therefore on the next day we will start with first order and second order characterization of a descent direction. Or once this descent direction characterization will be finished, immediately we will be ready to find first order optimality condition and second order optimality condition. In first order optimality condition, we'll have the Fermat's rule that if the function f is having a local minimizer at a given point x bar, and if the function obviously is differentiable, then the gradient value must be vanishing. The gradient vector must be a null vector. And from this necessary optimality condition, we'll have several interesting observations. And interesting observation means that this is really a necessary condition, but it will be not a sufficient condition. Towards that, several notions will come out, like you will have the notion of saddle point, and afterwards if directional derivative is greater than equal to 0 for any given direction, for along any direction from a given point x bar, then we will see that there might not uh, be a local optimality, and several other analyses are going to come out. Those are very interesting and surprising although. So on the next day, the lecture will contain at first order and second order characterization of descent direction, and then you will have first order and second order characterization of optimality or minimizers, and in between we will have a notion called saddle point, and a sufficient condition for a point x bar to be a saddle point also will be considered to be discussed. So these are the three things which will be discussed, which are going to come in the next lecture. Well, let me stop here, and I put my sincere thanks for all of your kind presence. Thank you. Thank you all.